Hello, friend. My name is Derek Harder, and in today's video, we're going to continue talking about generative AI, and we're going to be looking at some more techniques for generating images. So, in fact, image generation is, just as kind of popular as text generation. And we're going to be looking at a technique where we learn a latent visual space and we sample from it, okay? So in reality, some of the things I said before, this is probably the closest to modern image generation systems that you might be familiar with, okay? So the basic idea here is we need to first learn a latent space, okay? So you know what I mean by a latent space. It's the same idea as like the word embedding spaces that we learned for a textual space. In a language model. So the same idea, we learn an embedding space of a visual like set of images, okay? And by the way, this can be done. It doesn't have to be for images or text, So any kinds of things you can conceptualize as a space, you could learn a latent space like this, okay? But for image generation, you learn sort of embedding latent space, and then to generate images, you're going to sample from that space to create entirely new images, right? So if your space that was learned is dense enough, any point inside that space is going to be a valid image that's an interpolation between others in some particular direction or vector within your latent space. Okay? So in this section, we'll look at variational autoencoders, which I think are a little bit more successful in commercial sphere. So these are probably techniques like these are the things that are being used for image generation, the impressive kind of image generation systems that we see. And also in the next video, we'll look at GANs, generative adversarial networks, which tend to be a little bit more academic. So they both can kind of have some similarity in that they are going to be sampling. They're going to be creating a latent space and doing something to sample from it. Okay, with that, let's get started. Let's look at the variational autoencoders and how they work. Okay, so the key idea of image generation is to develop a low-dimensional latent space of representation, so a vector space, okay? So where any point can be mapped to a valid image, all right? So again, this is a very similar concept to the word embedding space and the embedding layers that we've seen before, okay? In fact, those are doing something similar to the autoencoder technique that we'll look at in this video here. So the module capable of creating that sort of a mapping, those are called generators in the context of GANs, generative adversarial networks, or in this video today, those are the decoders in the case of variable autoencoders, okay? So GANs and VAEs are two different strategies for learning such a latent space of image representations. They have their own slightly different characteristics. So the variable autoencoders we'll look at here are great for well-structured latent spaces. So if you have spaces that are more continuous and well-defined, a VAE is probably going to be a better choice. GANs can work really well, but they're very finicky to get trained correctly. So you can get really highly realistic images from a latent space, but the spaces don't necessarily have to have as much structure. So another idea that should be familiar are the idea of concept vectors. So we had the similar idea we've already discussed in terms of embedding spaces for word embedding spaces. So a concept vector given a latent space of representations, or an embedding space, means that there are certain directions in a space that might encode interesting axes of variations in the original data. So as a simple example from our textbook, if we have an embedding space of images, there might be a vector that encodes a smile vector, context vector, for example, like a smile vector. So what that means is that if there is such a vector, there is such a direction in this high dimensional embedding space, adding the smile vector onto some image z. So if the smile vector is S, if we add that vector onto an existing image Z, that will move us into space to another image that's a perfectly valid image that we would recognize, where the representation of the person in that image will be smiling, right? So I guess this is supposed to represent S being added on a little bit in that direction to, an extreme amount in that direction. The other one looks like it's meant to be like a frown vector, corresponding thing, but going in the this may or may not be the opposite direction from S, but a similar kind of frown vector, right? The variational autoencoders, they're a kind of generative model that's especially appropriate for the task of image editing. Be these kind of concept vectors that we talked about. So they're basically a similar idea to what are known as autoencoders, which are an old idea in neural networks. Okay, so the basic idea of an autoencoder is that it takes an original input, like an image, through an encoder process that will we force it to create a representation that's low dimensional. Okay, so it has to, the original autoencoders thought of this as compressing or putting it down to a compressed representation here. For example, if you think of these, we're going to be using MNIST images again for our example for the VAE here. So if this is an MNIST image, it's 28 by 28 pixels. So that's actually, if we flatten that, you can think of that as having, as originally, has a 784 dimensional space of pixels that, if we normalize them, go from 0 to 1, right? So the encoder might compress this down to 64 dimensions, so 32 dimensions or something like that. So we might force it to encode down to some low dimensional space relative, say 32 dimensional space. And then we also have something that reverses that, which would take something in 32 dimensional space and output a reconstructed image, right? So the classic autoencoder is a type of unsupervised learning, because you don't have to have any labels or anything to create this latent compressed representation here. So you can just build an encoder and decoder, and your loss function is going to be that the process, the output, should be as close as possible. So, a loss of 0 means that your output image, after it goes through compression and decompression, is exactly the same as the input image, right? So you don't need any labels or anything. It's unsupervised. You can just give it a set of images. It'll learn a compression as best as it can, a latent space that it can reconstruct. And if this is done well, if you set this compression well, that latent space will be useful as an embedding space, like we're talking about. So in practice, these classic autoencoders, they kind of work, but not as well as people would like. So variable autoencoders really kind of augment the idea with a little bit of statistical magic. And we won't go into it too much, but for purposes of you kind of understanding what's going on here, basically what's being done for a variable autoencoder is that they're forced to learn a continuous, highly structured latent space, which makes them much useful for this type of image generation. Okay, so instead of compressing its image into some fixed dimensional coding, it turns the image into parameters of a statistical distribution. Okay. And again, I don't know if you have to be too hung up about the details. And you'll see an example of doing this using regular convolutional layers here in a moment, right? So in our case, we're just going to turn it into a mean and a variance of some statistical distribution. So how a variable autoencoder works is the module turns the input sample, the image, into these two parameters in some latent space representation, the mean and variance. And then when we're so you sample randomly a point from that latent normal distribution, and you assume that it's assumed to generate the input image via the statistical property, the mean plus the variance times some bit of noise, epsilon. So the decoder module then in this variable autoencoder maps this point in the latent space back to an original input image. Okay? So the continuity combined with the low dimensionality of this latent space forces every direction in the embedding space to encode some meaningful axis of variation. So usually any direction you take, you can kind of interpret what's happening to the modifications that are being made between 2 points in the space here. So the result is these latent spaces are much more useful and very structured than the original classic autoencoders, the way they worked. So just to summarize that real quickly, the encoder decoder for a variational autoencoder, instead of compressing the image like a classical autoencoder, turns the image into a 2 parameters, so we'll just be using 2 parameters, which defines a distribution over the latent space, defined by that image mean and image, the log variance of the mean. And that gives us something that we can randomly sample from that distribution that the decoder can take and reconstruct the image from. So in like Python, like pseudocode, the encoder-decoder process might look something like this. Right? So the encoder outputs parameters over the statistical latent space, and then we reconstruct the image from those parameters with the decoder. Okay, so basically, get a little bit more concrete here. The reconstruction loss is simple, right? So this is unsupervised learning. So the basic loss is the same as the classic the classic autoencoder. So it basically forces decoded samples to match the initial inputs. That's the basis of our loss function, with some regularization loss. So this is kind of forcing it to be a well-rounded latent distribution. So kind of a continuous space here. Okay, let's look at a simple example of implementing this using Keras. So implementing a variational autoencoder. So we're going to be implementing it using the MNIST digits, like we talked about. So relatively small kind of latent space we'll create here. So we have to have 3 parts: an encoder network that will take an image and convert it into that mean and variance in a latent space. A sampling layer that takes one of those mean and variances and uses them to sample a random point from the latent space, and then a decoder network that turns the point back into an actual image. Okay. So let's look at the encoder network first here. So this basically is going to take an input image, an MNIST image, so say 28 by 28, that we have normalized. So it's going to be using a pixel value from 0 to 1 here. So this is mostly a normal convolutional network, although we're not using max pooling. We're using striding for samples. So that is because max pooling it's preferable to use strides instead of max pooling, where we care about information location, and we definitely need to kind of care about information location in this autoencoder here. But otherwise, the features go up, but since we're using a strided 2, this will go down to 14 by 14 and 7 by 7, since we're using padding same here. And then we kind of flatten it out to 16 dimensional, and then at a final, there's actually 2 outputs from here. So both of these will be 2 dimensions. So we just have a 2-dimensional latent to represent the mean and the variance for the embedding space that's going to be learned. So we can look at the summary of that So you can see how it goes down to 7 by 7, and then 7 by 7 with 64 features, so that flattens out to 3,136. And then we have actually two outputs, the mean and the log variance. Okay? Next, we need, we'll use a custom layer that will take one of these means and the log of the variance and draw a batch of samples. Okay, so here, we're directly what's coming in. So actually, batches will come in. So the dimension 0 is the batch size, and then we could use more than 2 dimensions here, but whatever the latent dimension size is, we get that from the first parameter here. And then we just create some epsilon at random using a random normal generation here, and that calculates. So basically this is kind of being compressed again, although compressed through this sort of statistical process here that I'm not going into all the details of. But the result of this is coming out as like a single vector. Okay. And then the decoder does the opposite. Okay, so it's going to take this as an input. So this is really going to be like a 2-dimensional vector. So the very first thing it has to do is inflate that back out to the last flattened layer that we had. So the last flattened layer that we had in here, when we went through the convolutional layers, ended up having 3,136 size, parameters in this flat. So we immediately take that out to the 3,164, and then we do convolution 2D transposes. So reshape it to 7,764, and then go through the reverse process using strides again and padding same. So the result after all that is we end up with a final output that's the same size as our input images in the MNIST database, right? 28 by 28 by 1. And that's what comes out of the decoder model. Okay, so now we're ready to create the variational autoencoder model itself. So we're not using supervised learning, as I already mentioned here. We're using a form of unsupervised learning. So it's common to subclass the model class if we want to stray from supervised learning, which is what we'll do here. So notice we're just going to, we need those 3 things, the encoder, the decoder, and the sampling layer that goes in between. So we have an instance of each of those. And we're going to set up some metrics. So we're going to actually track 3 kinds of losses here. The total, well, really 2. The reconstruction and this KL loss will be added together to get the total loss. So we're going to be optimizing on the total loss, which is a combination of these 2 losses. So, the secret sauce of the variational autoencoder is going to be happening here in our hand-built training step, right? So this is called externally, for multiple epochs. So this is just a single training step again here. All this happens inside of the gradient tape. So, we're basically doing the forward pass through here. So, we start with the encoder for an input image to get that mean and log variance. The sampler then sampling layer will turn that into a single vector, and then that gets passed through the decoder, right? So, these things, the parameters in the encoder and the decoder weights are going to be modified, which is going to end up representing this latent space. Okay, so from that, we're going to be calculating the reconstruction loss. The reconstruction loss is just a binary cross entropy. Okay, so when we're doing binary classification, this is just the difference between the input image and the reconstructed image, right? So since the pixels are 0s or 1, we want the loss to be 0. Like if the pixel was supposed to be a 0, we want the loss to be 0 if the input and the reconstruction were above 0, and we want the loss to be high if it was supposed to be a 0 and an output of 1, right? Vice versa if it's a 1. So if you recall, that's what binary cross entropy does. So this is doing the same thing we would do if we were doing like a binary classification. I won't go into this callback Liebler loss, but that's kind of the secret sauce for the variational autoencoder version. So this is a second loss. We just add those together for the total loss. Again, and then we're returning. So when we return these as a metric, so you'll see when we run this, we'll see all of these, what the total loss and the reconstruction and then this KL loss are as we're optimizing over the network here. So let me make certain I actually ran everything. So let's go ahead and fit our autoencoder. So since we're doing unsupervised learning, we don't need test and training sets. So here we load our usual MNIST data, but we go ahead and just concatenate everything together. So we just got one set of all of the MNIST images in the training and test set. And we create our VAE. In this case, we're going to use the Atom optimizer and perform 30 epochs of those training steps that we had in our training step method. Okay? So this will probably take 30 minutes on GPU here, but I'm going to try to let this run to completion here. So, okay, once that's finished, just a couple of notes about this. So you will notice the total loss should go down, although it'll probably hit 150 usually within 10 epochs, and maybe go down a little bit. Another thing that seems to be usual, you'll notice that the KL loss actually kind of stops and hovers around like 3.8, maybe goes up and down a bit, right? So the reconstruction loss is going down. Remember, we're just simply adding these together. So the overall loss is improving, but the KL loss seems to kind of hit a particular plateau. Again, if I didn't mention it, this is sort of the secret sauce. I don't really go into the details of this, but this is implementing, it's a kind of measure of how close your distribution is to like an ideal distribution. So, I don't know, I suppose if we could add in like a modifier to make it more important or make the reconstruction loss less important, right? So instead of just directly adding these up, put in like an alpha parameter for these. So I suppose, if you made this bigger, it would force it to make the latent space even more of like a regular probability distribution. I believe that would be the effect. So to get an idea of kind of what this does then, so again, what am I looking for? When you run this forward here, it forces it to go down into basically 2 dimensions. So Z here is really just 2 dimensions, since we define that as the size of the latent dimensional space, right? So we can visualize, since we got it down into this 2-dimensional representation, we can visualize every place in this latent space that was learned by, that's all we're doing here at the end. So we iterate over X and Y to go from like -1 to 1, and then we just plot. So we pull that out as our sample, and then we put it through the back part of the learned latent space, so the decoder part. So for every point on every 2-dimensional point over this grid from -1 to 1 on the 2 dimensions X and Y here, we pull out the sample, and we just ask the decoder to predict on that, and then we plot. And this is the result you get. So if you run this by hand, this will take a little bit of time. It has to do 900 samples. It's going to call predict 900 times here. So let's let that run and see what the result is that we get. Once that finishes, let me make this maybe a little bit smaller here. So we can see maybe most of the whole thing here. So you will get different results when you run this, depending on how samples are pulled out from the randomization of the batches, the initial random weights and things like that. But yeah, you often see something like this. So, but the idea is in our 2-dimensional distribution that was learned as the latent space here, there should be a smooth, you'll usually notice a pretty smooth transition between digits. I mean, there'll be some things that are a bit ambiguous. So you'll often see kind of like, and directions will mean a particular thing. So particular directions will mean oneness or nineness or things like that. So I don't know why. I often don't see like ones very, very well in these spaces. But yeah, you'll usually see things like from eights, directions going from like zeros to nines, things like that. But you know, I think the point is that the variational autoencoder, you know, the special sauce that is trying to force it to be a smooth probability distribution for the latent space, is you end up with something that pretty much at every point, you know, we sampled every point in the latent space on a regular grid here, and there are some that are a little bit messy that maybe aren't quite a regular, that look like a recognizable digit here. But for the most part, I mean, this is kind of showing that every place on the space, if you decode it, is going to come out to something that you would recognize as some particular digit, or maybe something a little bit in between two particular digits. Okay? All right. So that's it for our discussion here on variational autoencoders. So just a couple things you ought to remember about the things that we discussed on the section here. So image generation, one way to do it, and the way that probably the kinds of generative image generating systems that are most popular right now are doing it, is by creating a latent space. They might be doing it in different ways, but creating some kind of a learn latent space of the images that captures statistical information about, you know, your corpus of images. So, and then by sampling and decoding points from that latent space, you can generate never before seen images that are in those. So the two major approaches to this are the VAEs, the variational autoencoders we looked at, and the GANs, which we'll look at in our next video. So, so the VAEs, because of that special sauce of what they're doing, they result in highly structured, continuous, latent representation. So those are properties in many applications that you want. So they're a good choice for lots of applications that you can think of. Okay, so yeah, that's it for this video. Let's wrap this up here. Hope you'll stick around with me then for the next one, where we'll look at the GANs and how they work.